All right, chemistry, let's start our video lecture for chapter 7, section 2, talking about oxidation numbers. What I'm wanting you to be able to accomplish by the end of this section, I want you to be able to list the rules for assigning oxidation numbers. I want you to be able to give the oxidation number for each element in the formula of a chemical compound. And then I want you to be able to name binary molecular compounds using oxidation numbers and the stock system. All right, first up, we're dealing with oxidation numbers. Let's define what an oxidation number is. These are also known as oxidation states, so if you see them stated either way, they're the same thing. Oxidation numbers are assigned to the atoms composing a molecular compound or polyatomic ion that indicate the general distribution of electrons among the bonded atoms in a compound or ion. Now, this has its foundation in the difference between a molecule and an ionic compound, right? So we're describing the distribution of electrons. In an ionic compound, the distribution of electrons is such that the cation has lost electrons and the anion has gained electrons. The electrons have moved from one atom to the other. That is the distribution of electrons. And we use ionic charges to communicate that. But with a molecule, since we don't have a complete transfer of electrons, we simply have covalent bonds, the sharing of valence electrons. Therefore, we do not have full ionic charges. Remember, sometimes we do have partial charges, but never a full charge, okay, because we don't have ions. This is a molecule. And so we use oxidation numbers to describe the general distribution of electrons. So, rules. We got several of them. These are also listed in your textbook. Please make this list your friend. It's this slide and then the next slide. They're just rules to remember. That's all we're doing here. First off, the atoms in a pure element are assigned an oxidation number of 0. So something like O2 or H2. If it's just oxygen or just hydrogen, the oxidation number is 0. After that, we find the more electronegative element, which, remember, is going to be the second element listed. So the second or most electronegative element in the binary molecular compound is assigned the number equal to the negative charge it would form if it were an anion. Now, it's not an anion. This is a molecule, but if it was an ion, what negative charge would it have? You give that element an oxidation number equal to that same number. A couple of special situations. Fluorine, for example, always has an oxidation number of -1 because it's simply the most electronegative element. If we remember, oxidation states are describing the general distribution of electrons. If fluorine is the single most electronegative element on the periodic table, then no element on the periodic table is going to be able to outpull fluorine when it comes to attracting electrons. And so the electrons are going to lean closer to fluorine. And so in the bond that fluorine's going to make, it can only make one bond because it's main group 7, can only accept one more valence electron. That one electron is going to lean closer to fluorine, giving an oxidation state of -1. An electron is closer to it. Oxygen has an oxidation number of -2 in almost all compounds. Now, up in that first number right there, the atoms in a pure element are assigned an oxidation number of 0. When oxygen is just O2, its oxidation number is 0. What else? Oh, in a peroxide, which we'll talk about what a peroxide is in class, oxygen has an oxidation number of -1. When bonded with fluorine, however, it's going to have an oxidation number of +2. Okay, so those are some special situations, but oxygen in almost all compounds, except for the ones I just listed, has an oxidation number of -2. Also, hydrogen has an oxidation number of +1 in compounds where it's listed first, right, like the cation, and it has an oxidation number of -1 when it is listed last in a chemical compound. Number 6, the algebraic sum of all the oxidation numbers in a neutral compound is equal to 0, very similar to balancing ionic charges. Number 7, the algebraic sum of the oxidation numbers of the atoms in a polyatomic ion are equal to that ion's charge. So if that polyatomic ion has an oxidation number of, has a charge of -1, the sum of all the oxidation numbers within that polyatomic ion have to be equal to that same charge, whether it's -1, -2, +1, +2, whatever. The algebraic sum of all the oxidation numbers have to be equal to that ion's charge. And lastly, oxidation numbers can also be assigned to atoms in an ionic compound. That's fine. We're going to do that. However, just realize they're actually ionic charges. All right. Let's work through a couple of these. Let's go H2O. Okay. I don't see too many of my special situations. I don't see a pure element. I do see oxygen, however. It is going to be a -2. And so I have a total of -2 oxidation states here. So I need a total of +2 oxidation states here. There are 2 hydrogens to provide that. And since hydrogen is listed first, it's going to be a +1. And 2 +1s are going to balance my -2. I got sulfuric acid here. The first special situation that I see is oxygen, my best one. It's going to be a -2. Hydrogen is listed first, so that's going to be a +1. And so in order to balance all those charges, right, I have 4 -2s for a total of -8. I have 2 +1s for a total of +2. So in order to balance those out, sulfur has to have an oxidation state of +6. Let's see. Go ahead and press pause and generate responses for the last 3 sample problems. Go ahead and press pause now. All right, let's see how we did. Oxygen, special situation coming in at -2. That leaves nitrogen to be a +5. Oxygen, again, -2. There's an overall charge of -2 here. So that means sulfur is going to come in at +6. And the sulfate, right, also has an overall charge. Oxygen is going to be that -2, leaving phosphorus to be a +5. I have some more practices for you right here. Go and press pause if you'd like to try these. Otherwise, we're going to show you the answers so we can move on. All right, chemistry, that's going to do it for this part of the video lecture on oxidation numbers. I will see you next period.